Hi everybody, I hope this video finds you well. In today's video, we're going to be starting into Chapter 10, starting with Section 10.1. Chapter 10 is all about applying the calculus that you've been learning for this class and your Calc 1 class to different coordinate systems and different representations of curves. To start off with, we're going to spend a couple sections, 10.1 and 10.2, investigating how to do calculus on what are called parametric curves. In this video, we're just going to introduce the concept of a parametric curve and look at a couple of examples. Then we'll get into section 10.2 and actually learn how all the calculus that you've learned thus far applies to this new way of representing and thinking about curves. So, what is a parametric curve? Well, the definition is that a parametric curve is a curve where both your x and your y are defined as functions of another variable. That other variable is usually just denoted as t, and this t is called a parameter. So this t basically defines both your x and y. So when you're thinking about a parametric curve, you're still thinking about something that is graphed on an xy coordinate axis, but both x and y are sort of behind the scenes determined by a third variable, t, called the parameter. So, in other words, a parametric curve is represented by a pair of equations, x equals x of t, y equals y of t. So there has to be sort of two expressions that you need to define a parametric curve. You need to explain how x is determined based on the parameter t, and how y is determined based on the parameter t. So, parametric curves basically give us a way, instead of relating y directly to x or x directly to y, we sort of relate both variables, x and y, to a third variable, t, the parameter. Now, we're going to investigate mostly how to perform sort of the calculus operations that you guys have been learning for basically almost 2 entire classes, things like derivatives, integrals, all of that to these parametric curves. But for right now, what I'd like to do is just take a look at a couple examples of just understanding what a parametric curve is, and at least at a sort of brute force level, how you can construct a graph of them. So let's jump right in and take a look at this parametric curve. So we've got the parametric curve represented by x of t is t squared plus 2t, and y of t is t plus 1. What we're going to do is we're going to go very, very old school, way back to sort of when you first started learning graphing, probably back in an algebra class. And we're going to try to graph this parametric equation by using a table of values. And as we do this, not only are we going to sketch out the curve, but we're going to add one other thing, which is we're going to indicate the direction the curve is sketched out as the parameter increases. So in other words, one sort of common use of a parameterization is that it allows us to sort of not only get a graph of a curve, but also we can say, based on what value we're at in the parameter, where are we located on the curve? So if you think about letting the parameter increase, you can talk about not only what does the curve look like, but the direction in which the curve is traced out. So let's go ahead and start by making a table of values. So our table of values is going to have a list of t values, and then each of those t values is going to define an x value based on t squared plus 2t, and a y value based on t plus 1. So, since we don't really know what this is going to look like yet, let's just pick some easy t values to plug in. Maybe we'll do some things like -3, -2, -1, 0, 1, 2, 3. So that's a good amount. Those should be easy to plug in. Obviously, you're making a table of values, so you can choose anything you like. I'm picking integer values to make it easy to plug in. We'll get these, pop them onto a graph. If it looks like we understand the shape, we'll call it good and we'll just draw in the curve. If not, we can always go back and add in some additional values here. So if we have t equals -3, then if we plug that in here, that looks like we're going to have 9 minus 6, so that sounds like 3. And then when we plug in -3 here, we're going to get -2. So this will give us our first point on the graph. You can think about this as an ordered pair. So we're going to have the point 3, -2 on our graph. All right, let's plug in some other ones. If we plug in -2, we're going to get 4 minus 4, so that sounds like 0. And then here we're going to get -1. If we plug in -1, we're going to get 1 minus 2. So that sounds like -1. And if we plug in -1 there, we get 0. If we plug in 0, we get 0. And we get 1. If we plug in 1, it looks like we get 1 plus 2. So that's going to be 3. And if we plug in 1 here, we get 2. We plug in 2, we get 4 plus 4. So that sounds like 8. And we plug in 2 here, we get 3. And we plug in 3, we get 9 plus 6, so 15, and we get a 4 over here. All right, let's go ahead and we can just probably, we can fit it in right here. Let's give ourselves an axis, just like we normally would. Looks like the x values, I got a negative x value. I got all the way up to 15, so we'll need to be a little careful with that. The y value should be pretty simple, so I think for y, we'll just go ahead and label 1, 2, 3, 4, -1, -2, -3, -4. So I guess my scale there is just by ones. For x, I got to include -1 up to like 15. So I guess I could go by like 2s, 2, 4, 6, 8, 10, 12, 14, and 16. So we're going by 2s there. And I guess this guy would be -2 there. All right, so let's go ahead and graph these. So our first one was 3, -2. So 3, -2 would put us down here. Then we had 0, -1. 0, -1, sorry, there we go. 0, -1 right there. Then we had -1, 0, so right there. Then we had 0, 1, which looks like it's right there. Then 3, 2, so 3, 2 right there. Then we had 8, so 2, 4, 6, 8, and 3, so somewhere up there. And then looks like we had 15, so 2, 4, 6, 8, 10, 12, 14, 15, and 4. So it looks like we got that thing there. Now, if you think about this was t equals -3, this was t equals -2, this was t equals -1, this was t equals 0, t equals 1, t equals 2, t equals 3. So we're going from here to here, to here, to here, to here, like that. So at least if we were just drawing in the points that we had here, it looks like we would have something that looks like that. Now, does that mean that it ends here? Well, we didn't have any restriction on our parameter, so of course we could have done t values like -4 and -5, and if we wanted to, we could plug those in and actually see that you would get mirror images of this. So this thing actually does, it should be reasonable that it has sort of this parabolic shape like that, and if we wanted to indicate the direction that it was sketched, well, we were going this way. We went from here to here to here, to here, to here, to here. So as the parameter increases, we move along this way on the graph. So notice this is the first sort of extra piece of information you get when doing a parametric curve. This is a curve that you guys have probably drawn many times. It's a parabola, and we're actually going to prove in just a moment that it is a parabola. It's a parabola on its side, so it's a parabola in terms of y rather than x. But the extra piece of information that you get with this parametric curve is that not only do you get the curve, but you also get the direction that we're moving along the curve as the parameter increases. In this case, we're moving this way, so as t gets larger and larger, we're following the graph that direction. So parameterizing a curve allows us to not only get the picture of the curve, but also indicate a piece of information like the direction we're moving along the curve. You can imagine why that's useful in application. A lot of things like video game graphics and other things like them make use of parameterization so that you can describe mathematically movement of an object. So parameterization, very, very useful there. Now, like we said, we sort of reasoned out that the graph sort of looks like this. This definitely looks parabolic. Can we actually figure out if it truly is parabolic? Well, we can. A way of doing that is a technique called removing the parameter. Now, removing the parameter in some ways sort of defeats the purpose because it sort of says, let's get rid of the parameterization, which, at least for our work, we're mostly going to want to stay with things parameterized. But removing the parameter can help you confirm that something that looks like a standard shape that you've seen before really is that shape, isn't just close to that shape, it really is that. So let's talk about how we would do that here. So this is not something we're going to be doing a lot of, but we just want to at least see it once. So is this really a parabola? Well, we can do something called removing the parameter. So to check this, we're going to remove the parameter. And what that means is we're going to use these definitions here to solve for an expression that only involves x and y. So keep in mind that we have x is t squared plus 2t, and we have y is t plus 1. Now, notice what we could do is we could take this equation and use this to say that t is really y minus 1. Well, if we know that t is y minus 1, we could plug that in here. And we could then get that x is y minus 1 squared plus 2 times y minus 1, right? That's just replacing the expressions of x in terms of t using the fact that t is equal to y minus 1. Now, if we go ahead and expand that out, we could get that x is y squared minus 2y plus 1 plus 2y minus 2. And notice that we could get that that is x equals y squared minus 1. And that right there, that is the definition of a parabola in terms of y. And if we had just started with this, well, then you guys could have very easily gotten this graph, right? We know that x equals y squared minus 1 would be a parabola that has been shifted down 1 unit in the y direction, and it would be on its side. So this is the idea of what's called removing the parameter. Removing the parameter is just a fancy way of saying, let's rewrite our equation for the curve, not including the parameter. So just in terms back to x and y. Now, like I said, for most of the work we're going to be doing, especially when we get into section 10.2, where we want to learn the calculus of parametric curves, we're not going to be removing the parameter. In other words, we want to learn how to work with things that are in parametric form. We don't want to sort of have to always rely on something's in parametric form, take it out of parametric form, and get it back to x and y. But you should realize that there's a direct connection between things that are written in a parametric form and things that are written in that standard relation between x and y. All right, so this was sort of just a warm-up example showing you guys how to make use of a table of values sort of approach, choosing different values of t, getting values of x and y, plotting those with that additional piece of information of making sure we sketch how the curve is traced out as the parameter increases. All right, let's take a look at a second example just to make sure we're very comfortable with this basic idea of graphing parametric curves. So we're going to consider the parametric curve represented by x of t equals t cubed plus 1, y of t equals t squared plus 2. This time we're going to give ourselves a little domain sort of restriction. We're only going to be thinking about where the parameter runs from -2 to 2. So same thing, we'd like to graph this using a table of values and then also indicate the direction the curve is sketched as the parameter increases. So for our table of values, if we stick with integer values, we sort of are restricted to these. Of course, again, we could always pick out some non-integer values like 1/2 or 1/3 or something. And if we feel like we need additional points to make the graph, we can definitely do that. But I always like to stick with the easy integer values to start with. Now, the x of t is t cubed plus 1, and the y of t is t squared plus 2. So we need to plug in and go ahead and get these. So if we plug in -2 here, it looks like we should get -7. If we plug in -2 here, looks like we should get 6. Plugging in -1, we'll get 0. Plugging in -1, we'll get 3. Plugging in 0, we get 1 and 2. And then plugging in 1, looks like we get 2 and 3. And then plugging in 2, we get 9. And plugging in 2 here, we get 6. Okay. So those are our starting sort of values. Let's give ourselves an axis. Looks like we can get away sort of just labeling everything by 2. So 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. So again, we're going to just use a scale where everything is 2. So our first value is -7, 6. So -7 for x. So that looks like that thing should be somewhere over here. So there we go. There's -7, 6. Then we get 0, 3. So we get something right there. Then we get 1, 2. So something right there. And then we get 2, 3. So it looks like we get something right there. And then we get 9. We need one more sort of line there. 9, 6. So 9, 6 would be over here. Okay. Now remember, you sort of want to think about this as like a connect the dots, right? This is t equals -2. This is t equals -1. This is t equals 0. This is t equals 1. This is t equals 2. So we want to go from here to here and then to there. So it looks something like that. Now you might say, how do we know that it doesn't sort of do something like this, right? I mean, how do we actually know sort of the way to connect these? And the answer to that question is right now, because we don't have any information about the sort of calculus of this, we actually don't have a great way of knowing exactly like the sort of type of curve we should use to fill this in. You can probably guess, just sort of visually, that the way to connect this is something like that. Trying to have the concavity face the other way, something that looks more like this, doesn't really seem to make a lot of sense. So more than likely, the connection should sort of look like that, and there should be sort of a sharp corner, and then going like that. Now, in our next section, when we get into 10.2 and we learn how to do the calculus of this, we'll actually be able to show why there's a sharp corner here, because we'll be able to show that there's a vertical tangent line. So again, graphing things is always a bit easier once you have a sort of calculus background. Right now we don't have that yet, so we're just trying to do it as best we can. But by the time we get into our next video and we start to learn the calculus of parametric curves, we'll be able to know for a fact that this thing comes in like a sharp corner there and then continues on. For now, we'll have to take that sort of on faith, so we'll sort of connect this there and then to there. So there we go. Which way is this traced out like? Well, we said this is the lowest value of the parameter, then here, then here, then here, then here. So we draw in our arrows sort of following down this way and then heading this way. So we follow this curve like that, come to this sharp corner, and then move up to here. So there we go. Now notice we do also close these ends. We don't continue on because we were given this restriction of the parameter. It's probably reasonable that if it didn't have this restriction of the parameter, it would continue just sort of like that, and it would continue coming in like that. But we wouldn't indicate that in this case because we were given that restriction there. Now, this is a sort of weirder looking curve. You could try to remove the parameter on this one. It gets a bit messier because to solve for one of these, you might try solving for x. You're trying to solve t in terms of x. It would introduce like a cube root and it gets pretty messy. So this is a good example of why we sort of want to keep things in the parametric form. It has a very easy expression in terms of the parametric form. Both of these are just polynomial things. We're very comfortable plugging in and cubing or squaring things and adding constants. Very, very simple. You can get a normal rectangular xy coordinate representation of this curve, but it is a bit messier than what we got here. So on this one, we're going to skip trying to remove the parameter, and we're just going to say, okay, let's keep it in this parametric form. We got a nice graph, and that should be good enough. At this point, we're basically ready to get into section 10.2 and start to learn how to do the calculus of these parametric curves, specifically so that we can make sure this thing really has a sharp corner there. But we've got one last thing sort of as a quick aside to talk about. One thing I would like to say is that another sort of use of parametric curves, besides getting this extra information of direction, and besides representing some things in a much simpler form, this guy, again, if you try to put it in an XY equation, is a much more complicated expression than what we had here. A sort of third use of parametric curves sometimes is to parameterize a particular piece of sort of a standard function. And just to give us a little practice with that, and also to give you guys a little bit more practice with the idea of removing a parameter, just in case we do encounter that, we're going to do just a quick set of examples where each of the parameterizations is going to give us a specific piece of sort of a standard graph. So let's go ahead and take a look at our sort of last example here. So for this example, what we're going to do is we're going to go through each of the following, and instead of trying to graph it as a parametric curve, we're going to remove the parameter, recognize it as sort of a famous or standard graph that we're used to, and then quickly sketch that graph. But the important thing is we're going to, as we do this, we're going to take a look at the impact that the type of parameterization has. And we're going to see, especially in some of the later examples, that the choice of parameterization impacts the piece of the curve that you're actually parameterizing. So let's go ahead and take a look at this first one. So this first one says we have this parametric curve, x of t equals negative t plus 2, y of t is t squared minus 4t plus 4. Now, could we just go ahead and graph this in its parametric form? For sure, make a table of values, do all that. But let's try to follow what they're asking us to do here, which is to remove the parameter and then just quickly sketch the graph based on our normal understanding of graphs here. So let's see if we can remove this parameter. We have x is negative t plus 2, and we have y is t squared minus 4t plus 4. Notice it would be pretty easy to solve for t in terms of x. we could say x minus 2 is equal to negative t. And then we can negate both sides and get 2 minus x is equal to t. Then we could throw that in here and get y is 2 minus x squared minus 4 times 2 minus x plus 4. We could expand that, and that looks like it would be x squared minus 4x plus 4, then minus 8, then plus 4x, and then plus 4. And then looks like a lot of things would cancel. We would cancel this with this, this, and this, and we would just get that this is y equals x squared. So, in other words, if we were to remove this parameter, it would be equivalent to the standard graph y equals x squared. Well, we know what that looks like. That's just a parabola, our sort of standard parabola. There we go. But we'd like to do one more thing. We'd like to indicate the direction the curve is sketched as the parameter increases. So as the parameter gets larger and larger, what happens with these components? Well, let's focus on the easier one, the x. As t gets larger and larger, x gets more and more negative. That means that we're moving to the left. So the way that we're actually tracing this curve out is we're going this way. So this gives us a parameterization of the standard parabola where you trace that parabola out sort of going right to left. And the reason for that, again, is because x is negative t plus 2. So the larger t is, the more and more negative x is, the more and more you are to the left. So we're tracing out this graph like that. Was there a different way to remove the parameter here? Well, actually there was. If you look back at this thing here and you recognize that t squared minus 4t plus 4 is a perfect square, you could have just rewritten this as t minus 2 squared. And then realize that this is just negative x squared, which of course is just x squared. So we didn't have to do it this sort of brute force way, but since this is how we did it originally, we wanted you guys to just see another example of that. Okay, so for our first one here, we removed the parameter. We got a very simple curve that we already knew what it looked like, so we could make the graph very easily. But we do have that still that extra piece of information, which is that we have that direction that the curve is sketched. Okay, let's take a look at another one. So now we have x of t is cosine t and y of t is sine squared of t. Now we could try the same thing. We could say x is cosine t and then try to apply arc cos, but that sounds pretty messy. So let's see if we can just simply remove the parameter based on these expressions. So keep in mind we have x is cosine t and y is sine squared t. Well, it would be nice if these both shared the same trigonometric function. So let's rewrite this guy. This is actually the same as 1 minus cosine squared t. Because of course, sine squared is the same as 1 minus cosine squared. That's just standard Pythagorean identity. But remember, cosine of t is x. So this tells us then that this is immediately 1 minus x squared. So this is also a parabola. It's a different parabola. It's 1 minus x squared. So it's an upside down parabola that's been shifted up 1 unit. But there we go. So we know what that looks like. We can start to draw that. Okay. So we put ourselves at 1 there. Should look something like that. Sort of an upside down parabola. But we need to be really careful here. Keep in mind that the way we parameterized x and y, specifically if we look at x, is we parameterized it based on cosine of t. Which means that no matter what t is, this x value is trapped. This right here tells us that we're sort of restricted between -1 and 1. Right? If x is equal to cosine of t, no matter what values we plug in for t, we only get things between -1 and 1. So this graph isn't quite correct because this needs to end at -1 and 1. So if we go back, we can sort of fix that up. Actually, right, we're only getting this piece of the parabola. And this, like I sort of mentioned earlier, is one of the other uses of parameterizations. If we wanted to describe the parabola, but only a truncated piece of the parabola, we can use a parameterization that limits x to between -1 and 1. So we're only getting this piece of the parabola where x is between -1 and 1. Okay, what about the direction that it's traced out in? Well, That's not going to make as much sense here because cosine of t, if we say start at 0, is going to start us over here at x equals 1. Then we're going to trace this way as cosine becomes negative, but then we're going to trace back this way. So since cosine is going to just oscillate between -1 and 1, this guy is going to have arrows facing this way, but then he's also going to have arrows facing the other way. So this is not a great one for describing the direction because this cosine of t is going to cause us to go back and forth over this curve an infinite amount of times. So the direction is sort of both ways here. Okay, let's take a look at another one. So here we have x of t is t squared, y of t is t to the 4th plus 1. Let's see if we can use a similar sort of trick here. Obviously, we could try to solve for t by square rooting x, but square rooting is one of those sort of risky things because it's only a partial inverse on the positive side. So let's be a little careful with that. So instead, let's recognize that this is really t squared plus 1, which means that if x is equal to t squared, y is really x squared plus 1. So once again, we've got another sort of parabola. Now we know that this is the parabola that sort of looks like that, right? Where it's facing upwards, but it's shifted up 1 unit. But let's think if there's sort of a domain restriction here. We parameterized x by saying it has to be t squared. Well, if it has to be t squared, then that means that x is going to be restricted since it's something squared. This tells us that x always has to be greater than or equal to 0. Right? It always has to be a positive or a non-negative value. So if we graph that, what we're going to be doing is we're going to be graphing y equals x squared plus 1, but only for x greater than or equal to 0. So in other words, we only get this sort of section. So there we go. It would only be this portion. Do we actually get this point right here? We do. It would be a closed dot right here because like when t is 0, x would be equal to 0, or notice that we said x greater than or equal to 0. So we get this portion here. Now, as t increases, well, as t gets larger and larger, that x will also get larger and larger, so the arrows are tracing out this way. So notice that this parameterization gives us a parabola, but it only gives us half of the parabola. So we saw a parameterization that just gives us sort of one portion of the parabola and truncates it on both sides. Now we saw a parameterization that allows us to get an entire half of a parabola, still infinite, but completely remove the other half. All right, let's talk about one last one here. So for our very last one, we have x of t equals e to the t, y of t equals e to the 2t minus 1. So same idea. Let's sort of see how we can rewrite this. We have e to the 2t minus 1. Notice we can view that as e to the t squared minus 1. So that means we really have y equals x squared minus 1. Once again, you guys know what that sort of looks like. That's going to be a parabola that's been shifted down 1 unit. What about this, though? What does this sort of do to our domain? Well, x being equal to e of t, e to the t always is positive. E to the t is always returning a positive value. So this means x will be exclusively greater than 0. And keep in mind, it can't be equal to 0 because there's no value where e to that value gives you 0. So this time, what it would look like is it would look something like this, just shifted down 1 unit, so it's down here this time. So it's looking like that. But instead of putting a solid dot here, we would put an open dot because we would never actually hit x equals 0. Once again, as t gets larger and larger, x would get larger and larger. So we're tracing this out in this direction here. Okay, so why did we do this set of examples here? Well, to be honest, a lot of the time, we're not going to be removing parameters. Like I kept mentioning, as soon as we get into the next section, 10.2, we always want to keep parametric things as parametric. That's the whole point of this section, is to learn how to work with things in parametric form. But the other reason is I want you guys to sort of realize that while algebraically, none of these were particularly hard to remove the parameter on, all of these, it's pretty easy once we sort of got the sort of rhythm of it to remove the parameter. The thing you have to be very cautious of is when you remove the parameter, you have to make sure you still go back and think about how that parameterization impacts the domain. So notice that in each of these, the way that we sort of parameterized x as cosine of t, as t squared, as e to the t, impacted the x values for our graph. So removing a parameter is not just as simple as doing the algebra, it's also thinking about how does that parameter impact the domain. And obviously we're getting very different pieces of the curves depending on the parameterization that we chose there. So just something to be very cautious about if you ever try to remove the parameter of a parametric function. For now, though, this wraps up our introduction to parametric curves. In our next video, we'll be starting into section 10.2 and learning how to actually do the calculus of parametric curves, starting with derivatives and second derivatives of parametric curves. In that, we'll also use that calculus to draw some more graphs. So we haven't just, these two examples we did in this video are not our only graphs, our only examples of graphing. We're going to actually do several more examples of graphing functions and parametric curves, because it becomes much easier once we have that sort of calculus-based operations.